This is lesson 2. We're going to discuss the p-series test and integral test today. In our last lesson, we looked at the geometric series test and the divergence test. And in those cases, we were looking for the actual value of the sum of those series. But in this lesson, we're mostly going to be concerned with whether or not the series converges to a sum, not necessarily that we have to find it. And one important point today is that the convergence test that we're looking at will have to apply to series that have positive terms. And here are the two terms we saw in our first lesson. The geometric series test basically said that the series diverges if the ratio is greater than or equal to 1, regardless of the sign. And the series converges if the ratio was somewhere between 0 and 1. And we could find that sum using this formula. The divergence test basically said that if the limit as n approached infinity of a series was not equal to 0, then the series diverged. So let's just kind of review those here on this example. You can see in this first one, this is a series where we can rewrite the term and see it as the summation as n goes from 1 to infinity. And if I pull out the 1/5 as my ratio, as my constant there, I have a ratio of 4/5 to the n power, because this can be rewritten as 5 to the n times 5 to the 1, and being in the denominator makes it 1/5. So you can see that the ratio is 4/5, and the absolute value of 4/5 is 4/5. So our ratio is less than 1, and we know that it converges. And because it converges, if you wanted to find the sum, you could find the sum by taking the first term, 4/25, and dividing it by 1 minus the ratio, and you would get 4/5 for the sum. In this case, we want to think about this as an n behavior model. So the limit as n approaches infinity of that expression, because the powers are the same, for very large values of x, we know that the function is going to be bounded at 5/2, so it's going to approach 5/2. And 5/2 was not equal to 0, so using the divergence test, we know that it diverges. While we're looking at the first few terms of a sequence of partial sums helped us with geometric and telescoping series, we're going to see many cases where that won't help at all. That means you'll need to be skilled at using all of these tests to determine convergence and divergence. And the rest of the chapter is going to walk us through all of these tests. We saw these in the first two, and we're going to see these today, and then the following will be in later lessons. So let's jump right in with this exploration right here. We want to use the integral test to allow us to compare a series to its integral in order to prove convergence or divergence. But before we do that, let's explore the idea by completing the table below for 1 over x squared. So if we had 1 over 1 squared, that would be 1, and 1 over 2 squared would be a 4th, 1 over 3 squared a 9th, and so forth up until the 5th partial sum. In the next part, they're asking us to use this image here. We want to draw the right-hand sum with 4 partitions over 1 to 5, and then find the value of that. So let's go back to that image. So if we started with a right-hand sum, we're looking at 1, starting at 1, and going to 5. And we want the right-hand sum. So the right-hand sum would be the rectangle that starts at 1 and ends at 2. So this one has an area of 1/4. And our second rectangle would have an area of 1/9. The third one would be 1/16. This one right here is 1/16. And then our final fourth rectangle would be 1/25. So using those pieces of information, our right-hand sum would be 1/4 plus 1/9 plus 1/16 plus 1/25. And I'm going to use my calculator to estimate that. Looks like about 0.464. But when we find the fifth partial sum of that sequence, that means I would go back to the table and add this first value. So that would be 1, 2, 3, 4, 5, the first 5 terms of the sequence, and adding 1 to that, we're going to get 1.464. So we want to compare that using the integral test. So in the integral test, if we find the integral between 1 and 5 of 1 over x squared, our antiderivative is negative 1 over x, and we're looking between 1 and 5. So we're evaluating that would be negative 1/5 minus negative 1, and that would give us 4/5 or 8/10 if you went to a decimal. So it's adding up to be about 0.8. These first 4 gave us 0.464. So just to explain here, if we look at the summation from 1 to infinity of our expression 1 over x squared, we explored that it could be found by 1 plus, starting at the second term, the summation of the series from 2 to infinity is going to be here. So this expression is less than this expression, and this is going to be the upper bound of the series. So if the series converges, the series is bounded, and if it diverges, the series is unbounded. And we saw that convergence is not affected by these first n number of terms, where we only looked at the first 5 terms in this case. In order to use the integral test, 4 things have to happen. We have to have a continuous function. It has to be positive. The function has to be positive. It has to be decreasing, and we're only looking at the interval from 1 to infinity. So we're defining the integral test here. If they either both converge or they both diverge. In other words, the integral test says if the summation from 1 to infinity of our expression converges, then so does the antiderivative from 1 to infinity of our function in terms of x also converges. They both converge or they both diverge. So we can use that and apply that here. We want to use that integral test to each of the series below. So in this first one, if we write the series as an integral, we would rewrite this from 1 to infinity, and instead of using the terms n for our summation formula, we're going to convert that to 1 over x squared plus 1 dx. And then because this is improper, we want to take the limit, and I need to have some dummy variable. In this case, I'm going to use t as my dummy variable for the limit as t approaches infinity, and we want to integrate from 1 to t for that expression 1 over x squared plus 1 in terms of x. So you can tell this antiderivative is one that we're familiar with, which was tan inverse or arctan, and we want to evaluate that antiderivative from 1 to t. So the limit as t approaches infinity for tan inverse of t minus tan inverse of 1 is going to be, so if you think about the graph of tangent is going to approach infinity as we approach pi over 2. And then tangent is 1 at pi over 4. So we have pi over 2 minus pi over 4, and grabbing a common denominator, 2 pi over 4 minus pi over 4 gives us pi over 4. So our series converges using the integral test. Now I applied the test right away. Ooh. One thing I did is I applied the test without checking my conditions, and we can do that quickly here to see that 1 over n squared plus 1 is definitely continuous. It is all positive values from 1 to infinity, and the function is definitely decreasing on that interval from 1 to infinity. Another way you could do that without the use of a calculator is you could let n be 1, and then n be 2, and n be 3, and so forth. And if we applied that approach, you would see that the values are 1/2, and then 1/5, and then 1/10, and 1/17, and they are definitely decreasing along our interval. So I should reinforce that I need to check those. In example B, we're looking at the summation from 1 to infinity of n over n squared. And again, I want to consider, is that function continuous, positive, and decreasing on our interval? So again, applying the rule without going to the calculator, if n is 1, we have 1/2. If n is 2, we have 2/5. When n is 3, we have 3/10, and when n is 4, we have 4/17. So we can see that the function is decreasing on that interval. So applying the integral test from 1 to infinity and changing the n variables to an x, so we're writing the integral in terms of x. We could use u substitution, and using u substitution for our denominator, we get 1/2 on the outside, and we're taking the limit, and again, I need a dummy variable. I'm happy to use t. You can use b or any other letter. We have the natural log of x squared plus 1, which was our u substitute, and we're evaluating from 1 to t. So I'm leaving off that limit as t approaches infinity from 1 to t, and then using the u substitution here. So we have 1/2 limit as t approaches infinity, and we're evaluating the natural log of t squared plus 1 minus the natural log of 2. So as t approaches infinity, this portion is going to approach infinity. So the entire antiderivative would approach infinity, and it is unbounded and divergent. So our summation diverges because our integral diverged. Let's explore why 1 over n squared converges, but 1 over n does not converge. And I want you to consider the following groupings of terms in the harmonic series 1 over n. So we could say that this one's 1, and then we have this first group, and a second group, and a third group, and a fourth group. And we want to show that the sum of each group of fractions in the series is more than 1/2. So turn off the video and grab a calculator, and let's get an estimate on those 4 groups. Did you get the same estimates as I got? We can see that each estimate is more than a half. And part B said, now let's consider the terms in this particular series, 1 over n squared. We already saw that in our graph at the beginning of the lesson. And you can group the terms after 1 in any way that you would like. And we want to show that no matter which way you group them, they are never greater than 65/100ths. And I looked at these first two, 1/4 plus 1/9. So 1/4 plus 1/9 is about 0.174, and that's definitely less than 65/100ths. If you want to consider the next term in that grouping and add those three, 1/4 and 1/9 and 1/16 is about 0.423, and that too is less than 65/100ths. So explain why the harmonic series never converges. And you can write something in your own terms in that space below. And using that harmonic series in part A, I said it this way. After the second term, every group of any 2n terms will have a sum that's greater than a half, because a half was the value of the second term. We saw that in the list. So all of this leads us to P series. A series in the form of a summation from 1 to infinity of 1 over n to the power p is called a P series, where p has to be a positive constant. So for p equals 1, the series 1 over n is called the harmonic series, and we just saw that the harmonic series diverges. So the P series says that we will converge if p is greater than 1, and if the power p is between 0 and 1. So if it is a fraction, our series will diverge. And if p is equal to 1, as in the harmonic series, it also will diverge. Okay, so let's give some of those a try. So determine whether the following series converges or diverges. And in this case, we see that we have the summation from n equals 1 to infinity of 1 over n to the 3/2 power. So my power is a fraction, it's 3 over 2, and that's larger than 1. And we can say that this series will converge by the P series test, since the power was larger than 1. So we had that fraction, our constant was a fraction, and it was greater than 1. In this case, we're looking at the summation from n equals 1 to infinity of 1 over n to the 1/3 power. And here our power is also a fraction. The power is a third. A third is less than 1. So in this case, we have a divergent series. And the reason our series diverges is because the power is between 0 and 1, and we're using the P series test. In example C, we have the summation from 1 to infinity, and our series is n to the 1/4 power. So our power again is a fraction. It's between 0 and 1, and our series diverges. But we can also show that with the integral test if we take the antiderivative from 1 to infinity of 1 over x to the 4th and use the rules where we have the limit as t approaches infinity and work the antiderivative here. So that would be x to the 3/4 power times 4/3 evaluated from 1 to t. So the limit as t approaches infinity of 4/3 t to the 3/4 power minus 4/3 would be, let's see, this would be to infinity. So infinity, and again, we've shown that the series diverges because it is unbounded. The series diverges. In part D, you can see the same thing again here. If you rewrite this integral to be 1 over e to the n power, then you see that the ratio is 1 over e, and e is about 2.718, so we know that's in between 0 and 1. So we should see convergence here. And the reason we're saying it converges is because this is a geometric series. And using our integral test, we have the integral from 1 to infinity of 1 over e to the x dx, which is the limit as t approaches infinity. And then the integral of e to the negative x is e to the negative x with a negative 1, evaluated from 1 to t. And the limit as t approaches infinity would be negative e to the negative t plus e to the negative 1. And this is going to be 0, and this one will be 1 over e. So our integral test tells us 1 over e. This is the upper bound of the summation. And our series converges. So both by the integral test and by the geometric series test, because our ratio was less than 1. And we said this was the upper bound. And if you wanted to actually know the sum, you could use the sum formula. So the a sub 1 term is 1 over e, and 1 minus the ratio was 1 over e. So this would simplify to be 1 over e minus 1. If we combine like terms, I made this e over e. Okay, in example E, we're going to have to use partial fractions for this expression. And rewriting our antiderivative from 2 to infinity, we have a divided by x plus 1 and b divided by x minus 1, using the idea of partial fraction decomposition. When we let a be 1, or when we let x be 1, we'll get b is 1/2. And when we allow x to be negative 1, then a would be negative 1/2. So what I want to do is rewrite this as the limit as t approaches infinity for the antiderivative from 2 to t. And I'm going to pull that negative 1/2 out in front and rewrite my integral to be 1 over x plus 1 minus 1 over x minus 1 dx. So when we take the antiderivative with the negative 1/2 here, we have natural log of x plus 1 minus the natural log of x minus 1, and we're evaluating from 2 to t. So evaluating from 2 to t, we have the limit as t approaches infinity of negative 1/2 natural log. Let's see, we could take that negative and this negative. We could put the x minus 1 on top. So t minus 1 over t plus 1 here. And then that would be, and then distributing that negative, we've got natural log of 2 minus 1. This would be in the numerator because that would be positive. And then this would be in the denominator using the log properties. So that would be negative. And then half is out there. So we have, let's see, what's that do? Negative 1/2 natural log. Let's see, this one goes to 0. So negative 1/2 natural log of 1/3. And that would converge because our answer is natural log of 3 divided by 2 using the properties of logs, because this would be natural log of 1 minus natural log of 3 using the log properties. So this is 0. That's our converging, our definite integral. That one was tricky. And then finally in this last one, about a little u substitution. So if we let u be the natural log of the natural log of n in this piece here, I believe this is going to be our derivative. And the derivative of the outside is 1 over natural log of n times the derivative of the inside, 1 over n. And that is this fraction 1 over n natural log n. So this piece is my du and this was my u. So if we use the integral test, and we're starting our lower bound at 3, we have 1 over u du, and that could be rewritten to be the limit as t approaches infinity. And I'm going to jump back to my u terms. Natural log of my u, natural log of x from 3 to t, which is the limit as t approaches infinity for natural log of t minus natural log of the natural log of 3. That's mind-boggling. Now, applying the limit as t approaches infinity, this portion grows unbounded, and this is going to be a number. So because this piece is unbounded, then our entire series is unbounded and therefore diverges. So a little messy notation, but that ends lesson 2.